Hi everyone, I'm Michael Shaponiak, and today we're going to talk about word embeddings, which really are an interesting area because they power the advancements of just about every application of natural language processing, but often don't get an awful lot of attention. So we're going to dive into that topic a little more deeply. A little bit about me. I worked about 6 years as a senior data scientist for a defense contractor doing primarily operations research. The company had a lot of contracts with various government agencies to obtain clearances for their personnel. And the security clearance process is rather complicated and cumbersome. And what I focused on was making that process more efficient and more profitable for the company. Before that, I spent about 7 years as a software engineer for a couple of small companies, mainly doing Java backend development. And I have 4 degrees actually. My first two are in chemical engineering, and I also have a BS in computer science. And the last degree I obtained was a master's in data science from Rochester Institute of Technology in 2024. And my capstone project dealt with using a large language model to assist in the development of a text classifier. And I provide a couple of links at the end of this presentation in the slide deck. If any of you are interested, go and check it out. What we'll cover today are 4 main areas. First, we'll look at a few important NLP tasks just to kind of get ourselves oriented around what types of things need to be done in NLP. And to solve those tasks, we usually need a machine learning model to get it done right. But before we could train a machine learning model, we have to do some text processing, and then we need to encode that text into some type of numeric form that the model can understand. And we'll cover that step a little bit. And then we will jump into some code and look at why, the kind of amazing things that word embeddings actually capture, and compare that to one-hot encoding, and also how word embeddings basically capture relationships between words as well as similarity between words, which one-hot encoding does not do. And then we'll compare 2 logistic regression models. One we'll build from one-hot encoding, and another that we'll build from word embeddings. By the time we're done, we should get a good feel for why word embeddings are really important and how to use them. So let's jump into a few important NLP tasks. The first one we'll cover is text classification. Then we'll talk a little bit about part of speech tagging, followed by named entity recognition. So text classification is something we're all pretty much familiar with. It comes in binary and multi-class forms, and the favorite example everyone likes to give of binary text classification is spam versus not spam. So you have a classifier that looks at all your email messages and determines whether it's spam, and if it does, it puts it in a spam folder, and if not, it puts that message in your inbox. And I don't know about you, but I've noticed over the last, 5 to 10 years that classifier has gotten really pretty good. I would say I don't pull things out of my spam bucket. That's something that's important more than, maybe 2 or 3% of the time at most. So these things have gotten much better over time. And we can thank word embeddings for part of that, as you'll see when we get further along in this presentation. A multi-class type of text classification would be, say you're reading an article and you want to determine whether it's technology, sports, fashion, or other, one of those 4 buckets. Anything over 2 would be considered multi-class. And basically, we'll use a little bit different cost function to do that type of classification, but it's very similar. We have lots of different models that we can use to do text classification. The simplest would be logistic regression, and we usually want to try this one first because it is the simplest, and for a couple of other reasons. First, it's stable and deterministic. So in other words, when you train a logistic regression model with one set of data, you'll typically always get the same result. And you can't say that with some of these other methods because they have a stochastic element to it. But these other types of models like tree-based methods and neural networks are actually more powerful. Tree-based methods like random forests and boosted trees are actually very good. They can get us some pretty darn amazing results. And of course, everyone's heard of neural networks. Those are probably the state of the art, and they're wonderful. And I've worked with them a lot. However, they're kind of a pain to use when you're first using them because they have a lot of hyperparameters, and it's easy to overfit your models as well. So you need to do things like regularization or dropout or things like all kinds of techniques in order to make sure that model isn't overfitting. So neural networks and tree-based methods come with a little bit more cost of complexity, if you will. But logistic regression is really good also as a baseline. So when you build a logistic regression model, you should expect your more complex models to do noticeably better than logistic regression. If it doesn't, you're probably not training your more advanced models well, and you need to take a closer look at that. So let's look at part of speech tagging. So that's a pretty basic task, which basically assigns a part of speech to every word in a sentence. For example, my dog also likes spicy sausages. It has 2 adjectives, 2 nouns, an adverb, and a verb. Now, this task by itself is not particularly that important. However, the reason why we're covering it is that it's usually a first step for a process that is very important, which is word sense disambiguation, which is just a fancy phrase that is telling us that various words sometimes mean different things in different contexts. It's things we know intuitively, right? So I need to go to the bank to deposit my canoe probably means that bank probably means that the sides of that river with a sandy beach, if you will. And if I said I need to get to the bank to deposit my check, well, we know we're referring to that institution which not only holds my money but probably the money of lots of other people. So that institution is different from the one that has water on both sides of it. So that's part of speech tagging. And the last task we'll take a look at is named entity recognition, which basically puts words and phrases into specific categories such as location, like person, place, or thing, that game we used to play. The typical tags excuse me, are location, person, term, date, things like that, and they give us a sense of the content of that article or text that we're looking at. So it's real important for content discovery. What is this text about? We could use it to identify a customer. We can use it to identify where that customer might be located. Things like that. Now that we have a few NLP tasks under our belt, let's talk about how we would achieve these tasks. So we're going to have to build some type of machine learning model in order to do any one of those 3: text classification, POS tagging, or name entity recognition. But the problem is that we have a machine learning model that doesn't understand text. So we basically have to convert that text to some type of numeric vector in order to train our models. So the simplest way to do that would be with one-hot encoding. And what that does is basically it assumes that each word should be treated as its own separate categorical variable. So let's assume for a minute that we have a vocabulary of 1,000 words. And that vector of 1,000 dimensions, each one of those dimensions corresponds to one of the words in our vocabulary. So what one-hot encoding does is it looks at a word and it puts a 1 corresponding to that word in the vector, and all the rest are zeros. And it does that for every single word in a document. Now when you've done that, you have a bunch of 1,000 dimensional vectors. Each vector has a 1 in it. Okay, that's not a single vector, it's a matrix, right? We have to somehow convert all those vectors to one vector as inputs to our model. So what's typically done is we use another model we refer to as the bag of words, and we take each of those vectors and we add them together. Or I should say this way, because I'm saying 1,000 dimension vectors, we have a whole bunch of them. We just add them all together and we get one 1,000 dimension vector. However, that vector now has the count of each of those words in the document, as kind of illustrated in this image here on the right. So now we have a representation of the document as a vector. And it's a very simple way to encode vectors, and so that's one of its advantages. And it also has a very simple means of encoding the document as well. So you go from words encoding and then you encode the document with those word encodings, and it's pretty straightforward. The cons is that the words in a one-hot encoded vector do not have any relationship to any other. In fact, they're Euclidean. They're all orthonormal. So they have no relationship to each other. They're assumed to be independent. And we know that words have relationships to each other. And we also know that there's relationships between words as well as word similarities, which we'll talk about in a minute. But so that's the cons of having one-hot encoding. Now we have another option here, and this gets to the heart of what we're talking about. Word embeddings are a different way to represent a word. So what word embeddings are is that we choose the dimension that we want to use, but instead of filling them with counts of words, which is what we did for one-hot encoding, we have a bunch of integers representing a document in a vector. Word embeddings are real vectors. So each one of those slots, each dimension in a word embedding is a real number. Typically, for glove embeddings, they're like between -2 and +2, something like that. But they go out to 4 or 5 digits. So they're a vector of real numbers. And you choose the dimension. And the nice thing about these things, as we'll see when we get into the coding section, is if you build them properly, they'll capture relationships between words, and which is really pretty cool. And like I said, you'll see this in a minute. We'll see similarities. We'll see similar words have similar vectors, and the relationship between various words are actually captured in a lower dimensional space. We're talking like somewhere between 25 dimensions or 300 dimensions versus, say, thousands of dimensions or the size of a vocabulary if you're doing this with a one-hot encoded set of vectors. So the cons of word embeddings is that you have to choose between whether you want pre-trained word embeddings, which I refer to as canned, or if you want to build your own custom embeddings. Each has its advantages. The canned, obviously pre-trained is easier to use. Custom might be what you need if you need to squeeze out every bit of performance, but it's a bit more work. And you also need to decide which algorithm you want to use. One of the first algorithms to come out was Word2Vec by Google, but a year later, in 2014, the glove algorithm came out from Stanford, and it's pretty awesome, which is what I used for my capstone. Okay, let's get into some code. and see how word embeddings actually work in the wild. For this part of the demo, I've created a virtual environment which you can recreate yourself from the requirements file from the repo, and you can also download the notebook. So let's activate that virtual environment. Okay, we've activated the environment. Now we need to go over to where the file is, which is on another drive. So I like to run Jupyter notebooks with the Jupyter Lab environment. You could also do it with Jupyter Notebook, but I like Lab. So I'm going to start up the Jupyter Lab server. Okay, this notebook has an awful lot of content in it, and I'm not going to be able to spend much time on much of it. So I'm just going to try to focus in on the pieces that we care about. So let's jump right in and look at word similarity. We talked about in the slides that in embedding space, we would expect words with similar meanings to be close together in embedding space. And this part of the notebook actually explores that. So in order to do that, we first need to get some embeddings, and I use the Glove 6B word embeddings, which are right here. This link right here, you can download it. And we need three functions. One to read in the embeddings. After we've unzipped it, then we need a function to return the embeddings for one or more target words, and then we also need a function that returns the word that is nearest to an input word in embedding space. So this first function is, you could write it yourself, and I highly recommend you give it a shot because it gives you a feel for the workflow. If you're in a hurry, you could just run the function. It's in the word embeddings module. So I'm going to run that to read it in. It takes a minute or so, so I'm going to pause. Okay, it's done reading in the embeddings, and we have 400,000 words. They're NumPy arrays, and they're 100 dimensions. And because that's what we specified, that's what we passed into the function. Okay, the next two exercises are basically the real important one here is the word and end function, which is short for word nearest neighbors. It uses this get vocabulary embeddings function. Again, both of these are in the repo. I highly suggest you give it a shot. Try to write these yourself. Again, they're not too hard, and I even give you a hint as to how to measure how close vectors are to each other. Use the logalg linalg norm function from NumPy. So basically, we're going to check how close the words money, loved, angry, happy, desert, and full are. We're going to pass those to the word and end function in this little loop. And we're going to have the function tell us what the closest word is to each one of these words. And let's see what that looks like. So it looks like for money, the closest word is cash, which is really good. I think it's very close. Loved, remembered, that looks it's not great, but it's not too bad either. Angry and furious, furious is really good, pretty close. Happy and feel, not great, but not horrible. Desert and deserts look like it took the plural here. Full and complete, that's really good. So it looks like we have good intuitive evidence, that actually a little empirical evidence that shows that words that have similar meaning tend to be closer together in this high dimensional embedding space. Now what's really cool is embeddings also capture relationships. So in this case, if we took the vector for king and subtracted queen, we would expect the result to be similar to if we took man, the vector for man, and the vector for woman and subtracted them. So that's just kind of an intuitive relationship, right? So if we actually manipulate this, if we rearrange this equation to take what's on the right hand side, put it over on the left, and then put queen on the right hand side, we get equation 1 here, which would be king minus man plus woman is approximately equal to queen. And there are several other relationships we could build in a similar fashion, and I write them down here. And we're just going to explore two of them. This one and son minus father plus mother is approximately equal to daughter. Now, let's take a look at this. Let's manually compute what's on the left-hand side of equation 1 here. And we do that at this line right here. So king, the embedding for king, minus the embedding for man plus the embedding for woman is going to be, hopefully, something close to queen. So we're going to take that embedding and put it into our embedding NN function and see what the closest vector to that stuff on the left-hand side actually is. And it looks like queen is the vector that's closest to the result of what's on the left-hand side here, which is pretty amazing. We could do the same thing for equation 4, and we do equation 4 is son minus father plus mother, son minus father plus mother, and that vector should be similar to daughter. And sure enough it is. So that's actually great news. That gives us some confidence and a good feeling that these things are actually words that have similar meaning are closer together Euclidean distance wise in that embedding space. Excuse me, that was similarity. We're talking about relationships. Now these embeddings are actually encoding relationships. So we can explore other relationships besides gender. I mean, we explore gender here, but we can actually look at other relationships as well, and you will see similar types of results if you want to play around with that. So now that we have a feeling for proximity of words that have similar meaning and relationships between words, let's take a look at logistic regression. And this is just a review of how the conditional probability is computed for the target given the features. And in this formulation, I use -1 and +1 as the labels instead of 0 and 1, because it makes using this equation a little bit simpler. And the data we're going to use is from the UCI machine learning repository, and the link is provided here. And I basically take Amazon reviews, IMDb movie reviews, and Yelp restaurant reviews, and I basically concatenate all those reviews together and create one file called full set. So we have like 3,000 reviews, and this is what it looks like. And so basically this code just makes the plots look better. Now the first thing we're going to do is read in that data and split out the reviews and the labels and compute the targets, which is Y here. And this is what is going to be between, is going to be either -1 or 1. Okay, and now we're just going to check that out to make sure that's what we expect. And yes, it looks like the targets are now between, are either 1 or -1. Now we talked about bag of words earlier, so I'm not going to go through that again. There's a more detailed example with a really small vocabulary of 7 words if you want to look at something a little more detailed than what I described in the slides. So now we have to convert our one-hot encoded vectors to a bag of word representation of documents. So, but before we do that, we want to take our reviews and we want to get rid of the digits and the punctuation and convert everything to lowercase. And this just gives us a check to make sure we're doing that. We're going to remove stop words. You can read about what those are. They basically don't add any information, so we remove them. And we take a look at what these look like after we've removed the stop words. Now here, in this section, we're actually going to start encoding, we're actually going to start building the one-hot encoded representations of each of the words in each of those reviews. And we're going to sum them up. And that's what this data matrix actually is. And it is going to be 3,000 because that's how many reviews there are, each row. And each column is one of the 4,500 words in the vocabulary. Okay? So now what we're going to do is we're going to split training and test sets, and then we're going to train a logistic regression model on the training set, and we're going to compute the probabilities on the test set, and then we're going to compute an ROC curve. And it's not too bad. This one looks like it's got 0.88 as the area underneath the curve, which isn't too bad for the. So we have a bag of words representation for logistic regression. Now we're going to do the same thing for the word embeddings. I gotta move along here. This is just some of the missing words, 126. These are just basically funny spelled words in the reviews, so we're not going to worry about those. This section describes a way to convert a document that's been encoded with word embeddings for each of the words. How do we create a document vector representation? And this is just one way of doing it with a min and a max vector and then concatenating it together. The details are described here, but we're going to do this with a 300-dimensional vector, and this is going to take a second to read in, so I'm going to pause while this is reading. Okay, the embeddings have been read in. We're going to get some statistics. Again, we already know that 126 are missing. Now we're going to encode each of the words in the document. Each of the words will be converted to a word embedding, and then we have to convert. Then we have to convert each of those documents with words into a feature, a document vector. And so we'll create the feature matrix. These are the features. So they're 600 dimensions. Again, they're stacked, a min and a max vector. So then now we're going to split training and test set with the embeddings, and we're going to build a logistic regression model. And then we are going to we're going to actually get the predictions, the probability predictions from the model. We're going to stack those predictions from the embeddings with the one-hot encoded results, so that we can build a logistic regression curve with both of those results. So when we take a look at this, we notice that the blue line is the bag of words, and the gold line is the embeddings. Now it looks like the bag of words does a little bit better, but that shouldn't be too surprising. It's basically not taken. The logistic regression model doesn't take advantage of the richness of the representation like say a neural network would. Okay, let's recap what we covered. We first started talking about 3 NLP tasks to give ourselves a little bit of context in which word embeddings would actually fit into the picture. We talked about text classification, both binary and multiclass, part of speech tagging, and how that was a first step to word sense disambiguation, and we talked a little bit about named entity recognition and what that was. Then we talked a little bit about the fact that machine learning models can't take text as input. It needs numeric input, and in order to get to do those NLP tasks and use machine learning models, we need to convert our text to numeric vectors. And we talked about one-hot encoding, which was the simplest way to do that. And we talked about word embeddings, and a little more deeply we went into those in the demo. And we talked about the pros and cons of each of them, of those types of encodings. Word embeddings actually, we found in the demo that they actually encode word similarities as well as relationships between words. And when we went into our logistic regression model, we built one from each set of encodings, and we found that the results were pretty much the same. And we know why that word embeddings didn't do much better, because logistic regression was not designed to actually take advantage of the fact that it had all that wonderful similarity and relationship information actually built into it. And we also talked about custom versus pre-trained embeddings and the cost and the performance trade-offs. So I hope you found that helpful, and have a good day.